You guys we're going to have a M&M lab. I do like that our curriculum, after we have a break, we come in, we do a fun lab when we come back. And so now, and we do have no homework today, so that's good. All right, so let's take a look at page 1, chapter 26. So here's what's happening with this. In the past, right after Christmas when we came back, we did an M&M's lab where we were seeing what proportion of blue M&Ms you got. So we were just checking for one proportion, the proportion of blue, and we compared that to what the M&M's company claimed. Well, now we're going to not only talk about one proportion, we're going to be talking about all of the colors, not just one color of M&Ms, but all the colors of M&Ms. So what we're going to be making is a collective conclusion. So we're going to check the discrepancies of all the colors and total that up to see how that compares to what is expected. So I do want to point out to you that if you remember earlier in the year, these percentages are different because our M&Ms come from the Tennessee plant. So let's correct these numbers here. The brown, so right in there, the brown M&Ms, there's 12% brown M&Ms. The yellow M&Ms, there's 14% yellow M&Ms. The red M&Ms, there are 13% yellow. The blue M&Ms, 21%. And then orange and green are both 20. All right, so that's remember that we had discovered a few years ago that when the Tennessee plant opened up, it was different percentages, and I just haven't updated those notes. So what we want to do is see if, and so here's what our null hypothesis is. Are all the colors in the M&M's bag distributed as stated? And of course here is how they are stated to be. Okay? Or, the alternative hypothesis is then that the colors are not distributed as stated. So that's what we want to check and see. So that doesn't really sound too different from our hypothesis tests in the past, our null hypothesis and our alternative. But the difference is that this is not about one proportion. It's about multiple proportions. So if we want to do a test about multiple proportions, and we do collectively how we are doing compared to that, we do a chi-squared goodness of fit test. This is chi-squared. It's the Greek letter chi, and we end up squaring it, not chi like the hair product, okay? All right, so now let's take a look at this. The goodness of fit test is a test about whether the distribution of counts, FYI, we have to do our information in counts, although it is about proportion problems, or categorical, although it is about categorical data, we do our information in counts, not proportions. When we did a proportion test, we did them in terms of proportions. Now, it's about one categorical variable. What is our one categorical variable that we're going to be dealing with when we do an M&M's lab? What's the categorical variable? Very good. Our categorical variable is the color, the brown, blue, yellow, red, green, and orange. So that will be ours, and we're going to see if they are as predicted. So now, let's check our conditions. We do have conditions. This is not really one right here. This is just one that you need to kind of keep track of. Make sure that, as I mentioned before, your data is in number of items, the counts of how many items there are, not in percentages. Okay? If they are in percentages, then you have to turn them into the number of items. And then the next is get real. Well, let's talk about get real. We do check random sample just like we normally have. We do check independent just like we normally have. So random and independent are the same as in the past, but let's talk large enough. It is different. So for our large enough, that is the condition that is different than what we've done. And so here we go. Let's talk about the ones we have done in the past. For mean problems, How did we check to see if something was large enough? Take those off so I can. What is greater than 30? Your sample size is greater than or equal to 30. If it is greater than or equal to 30, then what was my conclusion about the distribution? I could say that it was, yep, approximately or nearly normal. Very good. Okay, and then we would have proportion problems. And so let's talk what the large enough condition was for those. What was the large enough condition for proportion problems? Yeah, what's greater than or equal to 10 though? Successes. Yeah, successes. So n times p is greater than or equal to 10, and q. N times q, or 1 minus p, either way, is greater than or equal to 10. And if those occur, then what can I say about that?
Nearly normal.
Nuh-uh. That one is the actual normal model. Remember, that one is z-curves and z-scores, so that one is normal. Okay, so finally, today, we've got chi-squared values, and so this is different. It is not a measure of sample size. It has to do with expected counts, and I'll explain that in just a second. The expected counts have to be greater than or equal to 5, and if that holds true, then our chi-squared model applies. And the chi-squared curve is different than the normal. It's different than the t-curve. It has its own unique shape, and we will be discussing that today. Now, let's talk about what this expected count is. Here is a picture of work I did several years ago when I first did these notes, and the information came from the Hackettstown, New Jersey plant. So these expected percentages are different than the Tennessee plant, which you're dealing with. But let's discuss what I did. So what I did a few years ago is I got my M&Ms and I counted them. They did total up to 60, and I figured out, how many was in of each color there were. That's my counts. Or you could also call that, the observed data. The observed, I know that's hard to see that right there, observed data. So then here comes what is expected. I need to see, if the percentages hold true that they tell me it should be, how many would I expect to get out of my sample size? So I would multiply the percent that they tell me, multiply that times my sample size. So this total number here is what you are multiplying those percentages by to get these expected values. So these expected values can be decimals because they are what you expect to happen on average in the long run. So if I collected many samples of 60, I'd expect to average about 7.8 brown M&Ms in those samples of size 60, and so on. All right, so that's what it means when it says expected counts has to be greater than or equal to 5. So did my information meet the conditions of large enough? Yes, because they were all greater than or equal. All of my expected counts are greater than or equal to 5. Okay, very good. So now, if you would, I'm gonna have you skip a couple of pages and go to page 4 where a blank chart is, and this is where you will be collecting your data. So on this page 4, what I want you to do right now, I'm gonna have you come and get your M&Ms in just a minute and do your counts. And then I also want you to figure out your expected. Now, of course, before you can get your expected, you need to know how many M&Ms you had, because that's your number, that you're multiplying the percentages by. Let me remind you what the percentages were. Brown was 12%, yellow was 14%, red 13%, blue 21, orange 20, and green 20. So there were those, and I would like to take a break and let you collect your data on your observed counts, and compute what you're expected. You could do those to 1 decimal place. So the next step is to do the formula, and let's kind of talk to you about what that formula is. So I wanted to point out to you your formula chart, the yellow formula charts that I have laminated. This is the front of it. And so if you happen to have not the ones that you picked up earlier, but the yellow ones that look like this. Also, if you have your student resources packet, it's in there as well. Okay, so there's the front of it, but look here. We are actually going to be doing stuff on the back of it, and we're going to be down here at the very bottom. So the very bottom of the back, because we are almost done, because that's the last thing we're going to learn on the formula chart. So this is the very bottom of the back of the formula chart, and so let's examine what this is. This is how we get our chi-squared statistic. It's also on page 3 in your packet. Yep. So the chi-squared statistic says you get your observed, what is your observed in our lab?
The actual count.
Yes, the actual count that you got. And you see how far away that is from what was expected to happen. So you're subtracting. But if I added together positives and negatives, I could get 0. And would that tell me an average distance away? No. So remember what we did with standard deviation? We did what so that it wouldn't add to 0? Squared it. So you're going to do observed minus expected quantity squared. And then we're going to do it in terms of the expected. So you're going to divide by expected. So one of these, you're going to do this for each color. And so for each color, that's going to give you the component, how far away each color is from expected. And then you will, what's this big symbol right here? You will then sum up all those 6 components, and that's how you would get your total chi-squared number. So let's go ahead and take a look at that on your little, on mine. This is what I want you to do. I do want you to write out the numbers you use just 6 times. I'm not ever going to make you do it again, but I wrote out my numbers, my observed minus my expected quantity squared, but you do it for your data and divide it by expected. And then you get your individual component. So you do that for each color, and once you do, you total it up to get the chi-squared value. And that's going to be your total of all those discrepancies. All right, so that's what I want you working on right now. Get your total of all those discrepancies. If you're still working on getting your total chi-squared value, that's fine. So you're still working on getting all these components, total them up to get your chi-squared. So I want to have a little discussion about this chi-squared number. And in order to do that, we need to take a look at what the chi-squared curve looks like. So everybody go back a few pages to look at what a chi-squared curve looks like. Page 2. A chi-squared curve is not normal. It's not even close to normal because it is not symmetric at all. What is the shape of the chi-squared curve? All of these are skewed right. Very good. Also, the numbers, the chi-squared value are these numbers at the bottom. So you would go like chi-squared value of 0, 1, 2, 3, and so on. What do you notice about these numbers? Whereas on a normal model is centered at what? 0. A normal model is centered at 0. Is the chi-squared model centered at 0? No, it is not. So it is not centered at 0. So that's another thing, because all of the values, all of the chi-squared values are what? Are positive because they are chi-squared. Okay, so they are all positive values. Now, let's take a look at how these change. Degrees of freedom will determine the shape of your particular curve. So degrees of freedom 1 looks like that. 2 kind of looks like that. You can see as we get degrees of freedom 3, 4, and 5, they're actually kind of becoming a little bit more what?
Normal.
Yes. So what happens is we say as the degrees of freedom increases and goes to infinity, the chi-squared curve becomes, I kind of hate to say more normal because it's still not going to be centered at 0, but I have seen AP questions that are multiple choice questions that did refer to it as more normal. It becomes, we can definitely say less skewed, more symmetric.
Or more normal.
Well, the thing about saying, you know, I'm going to put this in quotes because it's a little iffy. More normal is a little iffy because it's still not going to be centered at 0. So, but I have seen that on the AP exam as a question. All right, now let's talk about the degrees of freedom for our particular curves. So every single one of you had a different sample size in here. When we did T-curves, how did you know which T-curve to use for your particular data?
Degrees, the number
Degrees of freedom, which is n minus 1. So your degrees of freedom was n minus 1, and it is different for chi-squared. A chi-squared curve does not have degrees of freedom n minus 1. In fact, when we each got a cup of M&Ms, almost every single one of us probably got a different number of M&Ms, or very, you know, or not very many people got the same. For example, what was your total M&Ms? 75. Anybody else get 75 M&Ms exactly? Okay, so and so on.
I got
So
74.
how many?
74.
74.
I got 74.
74. Couple. 83. All right.
I got 60.
So we all had different amounts. Shh, listen up. We had different sample sizes. And in a normal model or a T-curve or in a T-curve, I cannot put all of y'all's data on the same curve because you would all have a different curve, a different shaped curve. Well, guess what though? In this particular problem, degrees of freedom are not n minus 1. Degrees of freedom for chi-squared are categories minus 1. And how many categories did we have?
6.
We had 6 categories because we had 6 colors. Brown, red, orange, yellow, green, and blue. So we had 6 minus 1. So our degrees of freedom is 5. So even though you all had a different sample size, I can plot all of your data on the same curve because we all had degrees of freedom 5. So I'm going to take just a moment and I'm going to put your chi-squareds on our chart on the board so we can talk about what that looks like, and then we'll summarize what we've determined. So before we talk about our picture, let's talk about how do we, when we run our test, and of course our null hypothesis is that our data is same, we can, you know, uphold the percentages that they claim, or we don't have evidence to reject it. What do we do to decide, what tells us to decide to reject or fail to reject the null hypothesis? The p-value. So I need to have a p-value so I can determine if I'm going to reject or fail to reject. So I want you to take a look at the chi-squared chart that you picked up. And let me get one that's more clear here. Okay, so this chi-squared chart, we're going to examine some of what we picked up here. Now, our degrees of freedom are what? Our degrees of freedom are 5. Very good. So here is our little line that we need to do because our degrees of freedom are 5. So we are interested in degrees of freedom 5. Okay, so we did have one person who had a very different information. His was out there at 21. So here in the middle, these are your chi-squared values in here. And so our one person who had a chi-squared value of 21, look at the vicinity of his p-value. His p-value was between 0.001 and 0.0005. So with that kind of chi-squared value, what would you choose to do?
Reject.
Yeah, so that chi-squared gave him a small p-value we would reject. Now, let's see, what is the chi-squared value? What's the biggest chi-squared you could have and still fail to reject? So what would our p-value be to fail to reject?
Yeah, 11.07.
Yeah, p-values. So this is the area that we fail to reject, of course, and then over here is when we reject in this vicinity. So this is our border, that's our threshold. So if you got a chi-squared value bigger than 11.07, you rejected. You had a very unusual sample. Did anybody have that?
How do you know that it's greater than 11?
Because our degrees of freedom was 5, and so that's why I'm looking on that line. And if alpha is 0.05, then when you have a small, because as chi-squared gets bigger, so let's talk about this curve. As the chi-squared gets bigger, what happens to the p-value?
Smaller.
Good. The p-value gets smaller. So that is one thing you need to know, guys. Look here. Because what would be the p-value? Say if this was if that was your sample, the p-value is the probability of getting that sample you got or something more extreme if your data is really centered or is really as expected. Okay, if you had a really low chi-squared value, if you had a really low chi-squared value of say 0, what would a low, Caden had the lowest chi-squared value I've ever had before. He had a chi-squared value of 0.1229. That basically meant that every single one of his colors was what?
Was it
Was supposed to be. Was as expected. That's right, because it's hard to say that they could, in fact, they couldn't necessarily be exactly as expected. Listen up, guys. Could they be exactly as expected in most cases? No, because your expected was decimals, and of course your observed is a whole number. But it's as close as it could possibly be to the expected. So here's another observation. In fact, I actually have a summary. Let's make some conclusions. So let's write these here. As chi-squared gets bigger, this is on that page 4. As chi-squared gets bigger, your p-value is getting what?
Smaller.
Your p-value gets smaller. Okay, we can also say the closer your chi-squared is to 0, the closer your what? Observed is to what? What you were expected to get. Very good. So the closer your observed is to expected, the smaller your chi-squared value will be. Okay, let's also review that degrees of freedom is not n-1, but degrees of freedom is categories -1. Okay, what do we also know about the shape of a chi-squared curve? Okay, chi-squared curve is skewed right. And they are all chi-squared values are what? Good. Yeah, are positive, greater than 0. Okay. Very good. So those are some conclusions and some of the different things that we've learned from this lab about chi-squared curves. Oh, one last thing. Hold on. When do you run this type of chi-squared curve? Yep, multiple proportions. Okay, now hold on a second. I got 2 minutes, and I guess I'll talk to you about the calculator part tomorrow. So multiple proportions, because I want to show you how you can get your exact p-value.